All right, everyone. So here we go. We're ready to continue on with QR. And what we've done so far is QR using Gram-Schmidt orthogonalization. And what I want to talk about now is a different way to do QR decomposition, which is through what's called the householder triangularization, which is a very clever way to do matrix decompositions, as you'll see. So this is about QR and the householder triangularization. Okay, so it was developed in about 1958 by Alston Householder, and he came up with this algorithm as a way to recursively sort of break down a matrix to do what we want to do, which is this QR decomposition. So first of all, I want to do two things. One is I'm going to develop the method, but number two is I want to contrast it with Gram-Schmidt's. Okay. Now, if you remember, our entire goal, right, is to take a matrix A and decompose it into Q and R, where Q is an orthonormal basis and R is upper triangular. And by having this form of the matrix, then I can do all kinds of things with it, which is I can solve AX equal to B. It also gives me some low rank orthonormal modes I can use to span this space of A. So there's a lot of possible uses of a QR decomposition, right? Both in terms of coordinates and in terms of solving AX equal to B. Now, what we did before with Gram-Schmidt is we came up with a recursive algorithm, and that recursive algorithm was such that we recursively built essentially rows of that matrix orthogonal spanning space Q. Okay? And so one way to think about what Gram-Schmidt did was it was basically constructing a series of matrices that are constructed recursively in order for me to build an orthonormal embedding space. So think about this. I took the matrix A, I figure out what do I have to multiply by R1, then by R2, and I do this recursively to start building the columns of Q. And this is exactly what we did in Gram-Schmidt. Gram-Schmidt was the first column of this Q is the first column of A normalized. Then I go through and I say, what's the second column of Q that's orthogonal to the first column? Then the third column, which is orthogonal to the first two columns. And the whole Gram-Schmidt procedure was essentially an iterative technique that did something like this. Okay? And so the idea behind Gram-Schmidt was this sequence of R values produces what is ultimately the inverse of the R matrix here. And this matrix has orthonormal columns, so that what you can do with it is you can construct R, which is equal to this sequence, the inverse of each one of these. Okay? And that is your R matrix, and that finishes your decomposition. Okay? And remember, this is the reduced QR. That's what I mean by Q hat, R hat. So this recursive formulation was just what Gram-Schmidt is going to do for us in its process of finding the Q and the R matrices that would produce this overall decomposition. Okay? And what we're going to see is householder triangularization is another iterative scheme, much like Gram-Schmidt, where we find one, find the next, and it's iterative, and then you span your whole space. And the question is, how is it doing it differently than what Gram-Schmidt is doing here? In fact, householder is going to take a different tact. What Householder is going to do is, instead of multiplying A by a set of matrices in order to produce orthogonal columns, orthonormal columns of Q, what we're instead going to do is multiply on the left of A series of matrices so that this is true. So notice the difference, shift in tact. Here, multiply on the right to produce orthogonal columns. Here, multiply on the left by these Q matrices. And by the way, these are going to be orthogonal projectors. That's why I'm representing them as Q, Q1 through Q of n. Multiply a bunch of by orthogonal projectors so that I can create an upper triangular matrix on the right. Okay, so this I'm going to call, Q star. Okay, Q star meaning that's its inverse transpose. It's the adjoint of this thing, so it's complex conjugate transpose. And so all the product of these matrices are Q star. And so once I have that Q star, it's trivial to compute Q, which is just complex conjugate transpose. And then that's going to give you A is equal to Q of R. Okay. So each one of these matrices is a unitary operator. And the product is also a unitary operator. And so I can produce this here. So the question becomes, how would I produce such an iterative set of orthogonal projectors, all unitary operators, okay, such that their product, recursively, I produce them to produce this full factorization of the QR decomposition, which is Q times R. But that is the goal. These are two different approaches for producing a QR decomposition. And the reason we might use this one, in fact, is often that this method here, this Householder triangularization, is very popular because it is, in fact, more stable numerically than Gram-Schmidt. And we will talk about numerical stability of these schemes as we go along, but not in this lecture. I'm just going to talk mostly about how to compute these things. So one way to think about what Gram-Schmidt is doing, it is a triangular orthogonalization. Right? So all these matrices here are going to be these triangular matrices that are trying to produce an orthogonalization on the right-hand side. Okay? So that's one way to think about what Gram-Schmidt is doing. However, Householder is doing orthogonal triangulation. Triangularization. Okay, so in other words, here instead, we're multiplying by orthogonal vectors to get a triangular vector. Here, I'm multiplying by triangular vectors to get an orthogonal vector. So they're just completely reversed in what they're doing. But it's important that you realize that's the main distinction between these two. And again, you could say, well, there's two ways to go about it. Why would I choose one versus the other? You choose typically a method based upon if it's numerically stable or which one is the most numerically stable, and oftentimes what's the computational cost. Okay, so Householder is very nice in the sense that it both is computationally nice and also stable. Okay, so that's going to be the main concept piece here when doing.
Professor?
Yes.
Is it more stable because Gram-Schmidt has to compute the inverse?
No, in fact, I'm going to get more into the stability issues later. It's not in Gram-Schmidt, we really never actually computed inverses, right? What we did is if you look at the Gram-Schmidt, we always just try to project into the next orthogonal direction. So there's no inverses computed during that process. This is just a abstract representation of what this is trying to do. But if you remember, if you look at the algorithm that we wrote down, both Gram-Schmidt and modified Gram-Schmidt was just all about producing a projector that projected it into an orthogonal direction to the ones I already had.
Right.
Okay. And this is just a different tact. This is now taking a set of orthogonalizations and producing a triangularization.
Got it. Thank you.
Mm-hmm. Okay, so I'm going to erase this, and I'm going to start essentially drawing the idea of what householder factorization is going to do for us. So the goal of the transformation is to recursively try to produce this triangular matrix by some orthogonal projectors. So let's take a matrix A. Here it is. Let's say it has 3 columns with some numbers in them. So the X means these are some numerical values. And what I want to do with this is I want to start producing a set of matrix multiplications on this matrix A that's going to start to make this look upper triangular. So here's the goal of what we're going to do. The first thing we're going to do is say, what happens if I have the first matrix Q1 times A? So what I want the Q1 matrix to do is to make all the zeros above this first diagonal, all the numbers below this first diagonal to be zeros. So I want to pick a matrix Q1 so that after this multiplication, those are all going to be zeroed out. And then you get some new numbers in the rows below. Okay, so let's call these X bars, because now you're going to change these from their original X's to some new values under this matrix multiply. So this matrix multiply, notice it left the top row unchanged. It zeroed out all these, and then it updated these 2 columns that are still there. Okay. Now what I want to do is multiply this by a new matrix Q2. Now I want Q2, Q1, A, and that's going to be equal to, what I want this Q2 to do is now make everybody here 0 above the next diagonal element. So I'm going to have X's across the top, 0, X bar, X bar. These are all going to be 0. And now I want zeros here, all below here. And now I have some new X tildes. So notice the 2 top rows were unchanged. Going from here to here, when I multiply by Q2, only thing that changes is I made all these zeros, and these got updated scores. Okay. Finally, what I want to do is hit it with matrix Q3. So Q3, Q2, Q1, A is equal to X, 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 0, X bar, 0, X tilde, and these are all zeros. That's what I want to do. And that's, by the way, my QR decomposition. In fact, it's the full QR decomposition, right? So normally when you have the upper triangular form, if it ended here, that would be the partial, but I've added the whole thing. I have all these 0 rows now down here. So it's a full QR decomposition. A couple comments. Doesn't this look a lot like Gaussian elimination? Remember, in Gaussian elimination, what we were trying to do is pick the pivot, make everything 0 below it. Pick the next pivot, make everything below it 0. Pick the next pivot, make everything below 0. That's essentially what this is doing, right? You're trying to figure out, how can I multiply by the next matrix? That one makes all these zeros, that one makes all these zeros, that one makes all these zeros. The question is, how do I find those matrices? And that's something we're going to have to address. And that's what household or triangularization does. It finds that matrix that allows me to do this. Okay. Second observation is, whenever I'm at some process here, like when I'm at this level here, at the next step, I am leaving the previous work alone. In other words, when I do this multiplication, it's really only acting on the smaller subsets. So when I hit Q1, I get this here. The next thing is going to leave everything alone except for these two columns. Next one's going to only work on these columns. So I want to leave the previous work alone. In other words, when I multiply by this Q matrix, don't mess up what I've already done. Leave that alone. Just work on the little piece that we need to do, which is add the zeros below that. Okay? So that's going to be the goal. Our goal is to determine, how do I actually construct this Q of K? And this Q of K, I want it to be an orthogonal projector. Now, we've already talked about orthogonal projectors in Gram-Schmidt. So we already kind of know how to construct them. So what we want to do is figure out, how do I construct an orthogonal projector that takes me from this matrix here, for instance, and it takes me this, and it basically zeroes everything out here, and then basically zeroes everything out there. So that's what we want to discuss next, is how to construct it. All right. So that's graphically what we want to do. So let's talk about the structure of the matrix we're going to need to make all of this happen. Now I'm going to write this down, and we're going to see that this is actually going to be a pretty nice little matrix that makes this all work out. What we want to construct is what are called householder reflectors. And what we're going to do is we're going to structure the form of that Q of K. And Q of K is going to look like this. The matrix itself is going to take this form. It's going to be an identity matrix up here, which is the K minus 1. If this is a K minus 1 by K minus 1 identity. You know what this does? It leaves all the previous work alone. That identity makes sure that it doesn't touch the columns that I've already set to put zeros underneath them, nor does it touch the rows that I've already worked with, right? So the work I've already done, leave it alone. I'm now at the Qth column. This is what this is going to be acting on. I'm going to go to Q of K is going to act on the Qth column. All the K minus 1 columns before, leave it alone. That's what this does. Just multiply it by identity, which means don't do anything to it. Okay? So all the magic is going to happen here in F. What do I want F to be? Well, F is going to be now at M minus K plus 1 by M minus K plus 1. Remember that A itself is M by N. Okay? So this is how many columns, rows I have left. So this is going to be size of this subblock. So one way to think about it is these are submatrices, right? Zeros, and these are zero matrices. There's an identity matrix of this size here, and there's this F matrix that's of this size. Now, here are some things I want for this F matrix. I want it to be unitary. Not only unitary, but I want it to be an orthogonal projector. Okay, so it's going to be kind of almost the same thing here. All right, so how do I construct? Well, that's easy. All I need to figure out is how to construct this F. All right, so let's go about it. I'm going to erase some of this and show you where we are with things. Okay, so that's going to be the form of this thing. So let me write this Q of K up here. Identity F 0, 0. That's the form that I want to take. And let's talk about what this thing has to do in this operation. Okay, so first of all, let's consider what we have so far. Up to this point, we would have constructed, this is the kth column. Up to this point, we've had already a set of matrices multiplying the matrix A. And so at this point, what I have is some numbers, 0, 0, and somewhere over here, I'm in the kth column where that's going to act. And at that point, what I have in this kth column, these are all x's. Okay? And in fact, all these rows over here are all full of numbers. So what I've done is I've zeroed out everything here. I've made this upper triangular up to here, up to the k-1th column. And what I'm trying to do is figure out, what's the next matrix I multiply this by so that what happens? So I make zeros below the diagonal term. Okay, so let's go to the diagonal term. Let's say this is it here. What I want to do is make all those right there, make those 0. Okay, so that's the diagonal. I'm putting that on the diagonal there. And then I want to zero out everything below the diagonal. A lot like what you would do again with Gaussian elimination. You pick your pivot, make everything below it 0. So let's call this vector here Xi. That's the vector Xi. So I grab this little subblock. That vector Xi is the same size of F. Okay, F, remember, is working only on this subblock. This identity is going to multiply everything above it. So the identity works on everything up here, leaves it all alone. F is just working in that subblock right there. And it's working in such a way to take this, and I don't care what's going on over here. I just want to make everything 0 below here. So if I call this the vector Xi, what I want Xi to be is just basically go from what it is to 1, 0, 0, 0, all the way to the bottom. Okay? So let's write this down in a better way. So that's what I got. That's my vector Xi. So my vector Xi is a bunch of values. And what do I want to have happen when F acts on this? When F acts on this, I want this thing to go to this vector right here. Okay? Or if you want to think about this, I can pull out the length of Xi as 1, 0, 0. This is the unit vector in this small dimensional space here, which is what is it? It's m minus k plus one dimensional space. This is the unit vector in the first direction. Or in other words, one way to write that is E1. That's the unit vector in the first direction of this subspace. So everybody go with this? This is what F does. That is what I'm going to try to construct an F to do, is take this vector and make it go from what it is to this. So I need to figure out that transformation. How does that happen? What is the F? What is the requirement on F to make that transformation happen? Because once I get that, then what I have is a way to recursively construct this thing, and it's going to make it upper triangular. And remember, this is generic. I picked K to be whatever. So this holds for every single one of those matrices, Q1, Q2, all the way to Q of N. Okay? All right, so let's talk about what we want to do in making F unitary. So there's also other constraints. Like there's a lot of transformations that could do this, but what else did I want? I want F to be unitary and an orthogonal projector. So there's constraints on how I want this to happen, right? In other words, you could probably come up, with some F that would do this, but the F wouldn't necessarily be unitary. I want a unitary operator that does this. Okay. So let's erase some stuff here, make a summary of what I want, and how to do it. All right, I'm going to leave this here, and I'll write down the summary of this. So I want F acting on the vector C, which is this vector here, to produce for me norm of C times E1. In other words, this is a unit directional vector. Hopefully you guys are okay with the, E1, E2, E3 are these vectors in three-dimensional space that look like this. Okay, so the unit vectors in each direction. So here it's the unit vector in the first direction of that of this m minus k plus 1 space. Okay, so that's all I mean by E1. It's like just like x dot, y dot, z dot, which are these unit directional vectors in three-dimensional space. E1 is the direction so that it's 1, zeros. Okay, E2 is 0, 1, zeros. E3 is 0, 0, 1, zeros. Okay, but I want it projected so there's a 1 here, zeros everywhere else. So that's the E1. That's what I want. Hey, by the way, I'm going to make a comment here. Why this direction? Why not minus E1? Or in fact, I could even just project more generally onto I could put some imaginary number in there that has unit modulus. In other words, I could project into a complex space on a unit circle in the complex space. So there's a generalization of this that can be done. For right now, let's just consider the plus sign, and we'll talk about that generalization a little later. Okay, so let's draw a space here. E1 direction, E2 direction, and this I'm going to just project it on two-dimensional spaces because that's about all I can draw. Okay, but what I'm really saying here then is I have this vector C. There it is. And what I'd like to do is project this vector C onto this vector. Okay, so basically, this is what I really want. I want the vector, I want the projection that takes me from here to there. Let's call this vector V. So the vector V is here. So here's what I have. I want to project it to there. And V itself is equal to this vector. So that's the difference. You just take this, subtract, you're down here. Okay. So that's the relationship between those. In other words, if I took this to the other side, v plus c would get me down to this vector. So this is this representation. So the problem with this is that I can easily do this, but what I really want to do is figure out a way to do it so that I have an orthogonal projector or a unitary matrix. That's the biggest constraint I have right now is I want to do this in such a way that every time I build this, every Q of K is an orthogonal projector and or a unitary matrix. The I's are super easy to deal with, right? I is already satisfies it. I don't have to worry about the I. It's this F piece of this matrix that I have to worry about. That's what we have to worry about here is how do I construct this thing so that in fact that thing stays an orthogonal projector for me. Now, we've already talked about what it means to have an orthogonal projector. And so what we're going to build here is basically this idea of like, well, there's no orthogonality here, but there is, in fact, a way to start thinking about it, which is think about this thing. Think about there being a hyperplane. H that separates, essentially makes this projection V allows this thing to, it's a space in which it allows this thing to be an orthogonal projector. Okay, so this is the representation of it, where if I have this point here, this point is a reflector or an orthogonal projection. Look at the way I've constructed this. Because it's a reflection, it means that this is orthogonal here. And this is in some sense the better coordinate for us to be working with. And no more than that, by having this hyperplane in which this thing is orthogonal, I can think of any point up here being reflected down here in an orthogonal way. And so this hyperplane allows us then to find a representation of this operator such that through this reflection, I guarantee for myself a unitary transformation or an orthogonal projector. So let's talk about what this projector might look like. We've already talked about projectors, P acting on Y. If you want it to be orthogonal, you just do something like this. This is the orthogonal projector to V, okay? And if you go back to the last two lectures, we talked about how to construct orthogonal projectors because we use them in the Gram-Schmidt orthogonalization. So, you know, what I'm going to encourage you to do is go back and review that because we've been using this idea of an orthogonal projector and then a complement of the orthogonal projector in order to build spaces for us to work with. Both Gram-Schmidt and this householder triangularization are going after the same thing, which is how can I use a sequence of matrix multiplies that have really nice properties to either get me an orthogonal basis, or in this case here, how can I construct orthogonal projections to construct a rectangular upper triangular matrix? And that's what this thing is starting to do for us. But notice this projector, by the way, isn't quite what I want. In fact, what I really want then is this PY will take this and project it down to this hyperplane. And on this hyperplane, everything's going to be orthogonal around it. But this vector C isn't just going to be a projection down to the hyperplane. It's not going to be just this vector. I have to go twice that distance to get over to this axis. You see that? This projection is going to get me from here to here. And I need to, and look how this is orthogonal, right? So this is an orthogonal projection onto this hyperplane. But I need to go that distance twice to get down to here. And so what you're going to do is basically say, well, this here is given by this guy. That's the projection along that direction. And so instead of going and normalizing by this, I want to go twice that distance. This is a unit distance down here. I want to go twice that distance. So what it's going to allow for us to do is construct F acting on Y. This is our projector now. That's what I was trying to find, is equal to 1 identity minus 2 V star over V star. V, that's thermal normalization, Y. There is my matrix F. This guy right here is my orthogonal projector. This is coming from this reflector. This is the household reflector. I take it, I construct this hyperplane, I do the projection, go twice the distance. I'm now done on this plane. And I've got myself a matrix F, which is in fact an orthonormal projector. Exactly what I wanted, which is the sequence of these Qs. These Qs have to be orthonormal projectors. And I just did it by this geometry. Okay? That's the way I can take a vector, project it into the direction I want. And when I do this, then it will project this onto C. It will project it onto exactly this. This thing here now turns into absolute the norm of C, all zeros below, in such a way that this matrix is in fact unitary. So that is the critical idea behind this householder reflector idea. Okay. By the way, I want to point out one other thing. So this takes a little bit of, I would say, pondering. So one of the things I would encourage you to do is reflect upon that was a pun I didn't quite intend, right? Reflect upon this. Okay, householder, reflect upon this. I'm sure you're all laughing. I just can't hear you because they're all on mute. But what you need to do is take a little bit of time and just think about what this means a little bit. Think about the geometry of it. Remember, I am not just looking for any matrix to do this. I am looking for very special matrices, orthogonal projectors. Everything's coming down to this idea of orthogonal projectors. And so you want to start thinking about that. And this is sort of a geometrical picture that's consistent with what we've been doing at Gram-Schmidt, and it's consistent with unitary matrices. Everything we've been building towards is trying to understand these things in terms of these really nice matrices that have great properties. Okay? But I also want to highlight one other issue in this, which is, when I do this, there's oftentimes the ability to, in fact, pick a sign. In other words, I could say, here's my vector C. And I could say, well, in this direction here, this is that. Or I could go this way to minus. What's interesting about it is if you choose to say, well, if I want to go and project down to here, my plane, my hyperplane separating it looks like this. However, I could, in fact, go this way. And then my hyperplane separating that is this. Let's call this H plus, H minus. Notice that I have then two possibilities. There's no reason that this is the right one. I could always just project to the negative sign, and I could produce the same kind of thing with a unitary matrix. More broadly, I could even put in FC is equal to zeta C E1, where this is just on the unit ball. Like if it's a complex number, I don't have to project it into plus or minus one. I could project it into some complex number space. Why would I do that? One of the reasons you might do this is just simply due to numerical stability. Suppose that, in fact, these two, this point and this, were very close together. All of a sudden, at numerical round-off, it's having a hard time distinguishing between C and epsilon 1. And numerical round-off is going to have a big role to play then in determining messing up your calculation, actually, the stability of the calculation. However, if I use this point, the cut is well spaced. I'm going to get a very nice cut line for that hyperplane. So oftentimes people will sometimes choose some different hyperplane so as to take advantage and exploit structure. Okay. All right. So that's the main ideas behind householder triangularization. What I wanted to do is spend just a few minutes walking through a code that I'm going to email you upon conclusion of the class. And this code is from Toby Driscoll. He wrote this. He did a really nice job with it, so I'm just going to use it. And it's a QR factorization based upon this right here that I just drew up on the board. It recursively computes these, and you multiply the A1 matrix at Q1 by Q2 by Q3 all the way to Q of K, or Q of N, to produce a QR factorization. So the nice thing is, I'm not expecting you necessarily to write this code at this point or be able to write it. It's you know, you can spend some time doing it, but I'm going to send it to you so you can actually see the structure of how this thing works. All right, so I'm going to do a screen share and go to my Matlab. Actually, I'm going to share my desktop. Share, and there we are. Okay, so here is my code, or here's the code from Toby Driscoll. So this is going to be called QR factor. So this is an idea is to represent what QR factorization is going to do for us. So what you see here is QR factor A. So I'm going to give it a matrix A, and what's going to be returned, so it's going to call a function, and what's going to return is Q and R. First thing you need to know is what's the size of the A matrix, right? M by N columns. So the first thing you do is do the size command. It pulls that out. You're going to first start off by taking this Q matrix and make it the identity. By the way, on the board, right, we know that the Q matrix, as we build it out, it's going to have identity plus those F matrices. So all I'm going to do is overwrite the identity with these little blocks of F that we construct. So all we need to really do is compute these reflectors. So here are the reflectors. I'm going to go through and I'm going to walk down every single row. So this is the K loop. The K loop is going to essentially walk down starting from the first diagonal to the next diagonal, all the way through all n diagonals, and make everything 0 below them. So at each step, I've got to produce the reflector. And here is the reflector. Basically, it's exactly what I wrote up on the board. There's the normalization for V. And so, you know, I'm not going to go into too much detail of this just because simply time is not on our side. But like I said, I'm going to send this to you guys so you can kind of look at the structure and compare it with the notes or what we did in class today. So here's how you find the reflector. Remember, this is that submatrix that you want to construct. The submatrix is given right here, right? So this is pulling out the right columns and rows for you to mess around with. And for instance, here is the normalization that you get. Here is where you want to project this. This is the V itself, how to project to the V. Once you have that, you apply it for each column. So now you go through and say, well, once I have this, I'm going to update my matrix by multiplying by this Q of K. Okay, so that's exactly what these set of codes do. And then you basically do this, and then you have this thing, and then you essentially look at returning the Q and the R. The A matrix was made triangular in this process. So what's happening at the bottom here is triu A basically makes it perfectly triangular. Q equals Q star. We actually produced a series Q1 through Q2, but remember, it was the transpose that mattered for us. Okay? So we transpose it, that's what returned. So here we go. I'm going to go ahead and make a matrix here. So the matrix I'm going to make is just here, a random matrix that's a 5 by 3. In other words, 5 rows, 3 columns, just some random numbers. So let's look at it. Here's A. Who cares what it is? I just took some generic matrix, and what we're going to do with this matrix is produce QR factorization. So now you can say, okay, pull in QR factor. There it is, runs the code. And here are your 2 matrices to get out. You have Q, here's the Q matrix, and here's R, the upper triangular form that you get out of this thing. So this is a really just nice, simple algorithm. You saw how fast it was, that does this QR decomposition using these triangular reflections. It's just basically taking those formulas that I wrote up on the board and recursively starting to construct Q1, Q2, Q3, all the way to Q of n here. And then that's going to be the code that produces for us a full QR decomposition that allows us to build, in a stable way using this householder triangularization. And again, people like householder because householder is pretty numerically stable, more so than Gram-Schmidt. And so that's why in practice, it's often used quite a bit. All right, I'm going to stop there because we're about at time.